My name is Simran Raval, and I'm a PhD student here in the Department of Astronomy and Astrophysics, and I will be your host for tonight. And I would like to begin tonight's event with a land acknowledgement. So this event is situated in Toronto, which is situated on the traditional land of the Huron-Wendat, the Seneca, and most recently the Mississaugas of the Credit River. The territory was subject to the Dish with One Spoon, One Thumb Felt Covenant, an agreement between the Iroquois Confederacy and the Confederacy of the Ojibwe and allied nations to peacefully share and care for the resources around the Great Lakes. Today, this meeting place is still home to many Indigenous peoples from across Turtle Island, and I'm grateful to have the opportunity to work on this land. Acknowledging the traditional territory on which we live and work is a small but important step that reminds us to learn more about the Indigenous peoples in these regions, to consider the history and ongoing colonialism on this land, and reflect on how each and every one of us can contribute to reconciliation. You can visit native-land and whos.land to learn more about the land you're on and who it belongs to. If this is your first time attending AstroTours, we generally run our tours on the first Thursday of most months. And after the talk, we'll be heading over to the physics building for some demos and also an opportunity to use the telescopes on the roof. This event is run by graduate students in the Department of Astronomy and Astrophysics, and our volunteers consist of undergrads in physics and astronomy. And we always want to make this event as great as possible. So after the event, if you could please fill out our feedback form at bit.ly/astrotours, that would be greatly appreciated, so we can always continue to improve this event. So tonight, we're going to be having a talk by Eesha, and then after, as I said, going over to the telescopes, and those will be open until 10:30. It's also June 1st, so this is the first day of Pride Month, which is why we've themed our slides this way. But before we get to today's event, I'm going to go over a few upcoming events. So next month, we're going to be having our talk by Taylor Kutra about protoplanetary disks. One thing to really note here is that it won't be the first Thursday due to a timing conflict for our speaker. So it'll be the third Thursday, July 20th at 8:30 p.m. in this room. Just keep that in mind. It'll be July 20th, not July 6th. You can always look at the Dunlap Institute Facebook page and website for more information on their Cosmos Cougar Couch video series. They will be releasing a Pride video soon as a part of that series as well. And you can also go to the Royal Astronomical Society of Canada and see all the different events happening in Toronto and around Toronto for astronomy. The Toronto website is listed right there. Another thing that I would like to mention is we will be hosting on July 26th an Age of the Universe workshop. This is for grades 11 and 12 high school students in the GTA, and they will get to learn the basics of coding and astrophysics and how we actually try to do research, and they'll get to use real data from different telescopes to be able to compute for themselves the age of the universe. We have some of our contact information there, and this QR code is for our website. The event is completely free. We will be supplying computers for the day, paying for food, transit there. So if you know any grade 11 or 12 students, definitely let them know about this opportunity. Great. So now, on to tonight's speaker. So Eesha Das Gupta is a PhD student at the Department of Astronomy and Astrophysics at the University of Toronto. She works on making computer simulations of stars to study how they rotate and how they would interact with companion stars. Eesha previously received her bachelor's degree in physics from Drexel University in Philadelphia. In her free time, she enjoys reading, drawing, and introducing people to niche subcultures. So I will now pass it off to Eesha to tell us about a rookie's guide to a DIY star.
Hi. Yeah, just to make sure people can hear me. Like, okay, or this is why I'm making sure people can hear me. Yeah,
Is it turned on?
I did tap it. Can people hear me now? Can people hear me?
You want to press it?
Yeah.
Maybe hold
Hello?
it down?
Can people hear me? Hello? Oh, yeah, as in to hear me louder?
A little bit louder now.
Yeah, here, can I?
Yeah.
The
Sorry.
light, the light is the wrong color, so I think something's
Okay.
happening.
You get the light to the right color and be right back.
I'm going to take the batteries out maybe.
Okay.
Put them back in.
Okay. Does it work now?
Right. Oh, maybe it's dead. Okay. There's extra batteries here.
Okay.
Sorry about that. Just 1 second, everybody. If it doesn't work, we can just use the podium mic.
Yep, that's fair. Is it working?
Lights that are color.
Does it work? Yeah. Oh, yeah. That's how voices sound on a microphone.
There you go.
Yep.
So,
That's fine. Yeah, so I am going to give you a really bad DIY video. And I'm sure you've seen lots on the internet, right? So you're not going to be like, it's not going to catch you that off guard, I hope. But like any DIY video, I'm going to start it off as this is a simple thing you can do in your free time, pick up a hobby or something. But it's going to evolve into like really complicated hijinks where half of it like gives you anxiety, and then you're like, man, I should have just bought this from IKEA, but then building IKEA furniture also gives you anxiety. Anyway, if you get lost during the talk, I just want you to hold on to this takeaway message that you cannot make a star in a lab. And that's why we're doing all this, or that's why we want to be rookies in the first place who try to make our DIY star, right? Like there's a point to this all. But this does beg the question, so what? Like why do we care if we can't make a star in lab? So I'm assuming because you're here, you feel enthusiastic about science, and you may have come across the scientific method before. Give me a shout out if you have. Yeah, woo, yes, great. So I heard many woos, but so like the overall process, you should be familiar with this, that you make an observation, you create a hypothesis based on, like essentially to reason out why that observation looks like the way it does. You do some experiments, test out your theories, you analyze the results from your experiment, and then you conclude. Very neat 5-step process. Astronomy is no exception. We also go through this process. Stellar astrophysics, which is specifically like study of stars, is also not an exception. And I'm going to walk you through each of these steps on how astronomy does it, all to make a point of like, we need to make stars, but you can't do it in a lab. So our observations basically come from telescopes. We have ground-based telescopes. We have space-based telescopes. You're gonna see a telescope tonight. You don't use that actively for research, but do teach courses in it where you can basically go through the whole step, do some analysis, conclusion, hypothesizing, and so on. But that's essentially how we get our observations. Once we have data to work with, we hypothesize why the data looks the way it does. And the key to do that is not come up with things from scratch like conspiracy theorists. No shade on conspiracy theorists. I respect them, but you should read papers to see if someone has done the same thing you've done before. It will save you a lot of time. You can work on new things. It will also save you some energy. I mean, you do spend energy reading the papers, but that's energy well spent, in my personal opinion. Then we experiment. This sounds absurd, but like put on lab coats, look at test, but well, our systems are that big. Like you see the Earth in there, like the labs are on the Earth, right? Like these scientists are in there, like on that small picture. Like I did put it there. I was honest. I will not lie to you. It's just really small. So you can't make stars in labs on Earth because they're, one, too big, two, too hot. So essentially, you can't reach those temperatures, you can't reach those sizes. Physics, the way they work, changes a lot depending on their size and depending on their heat, like temperature. So I can't just botch this and be like, oh, this is a star, this is small, but this looks like a star, so it's okay. I can't do that like in a lab space, right? But there is somewhere where you can make small stars. You can simulate them. So I'm assuming people are familiar with video games. You essentially simulate a virtual reality in your computer. This is similar, though it looks less pretty in a way. So it's, instead of like wearing lab coats and like looking at test tubes, we end up like looking like this. Working from home was great for theorists because we just had to like, we could do this in our pajamas. Yeah, so essentially the idea is to take that control environment that you would get in a lab and transfer it to your computer, right? But it doesn't look really neat. As I said, it just looks like this a lot of times. It's just a bunch of code. So you will have to learn coding, but we are rookies, and I am not going to like touch the subject of coding. Simran has a workshop for that if you're in high school, by the way. So we made a shout out before that. So if this pleases you, do join her thing. But yeah, so because we are rookies, we're not even going to do the controlled lab environment thing. This is going to be an oven fire in the kitchen level of DIY projects. We will still need to code, but let's look past that. But yeah, so let's cook up a star in a kitchen. So for most recipes, you need some substance. You need flavoring, like spices, seasoning, whatever. And you need something external, like you can cook it on a flame. You can mix it if you're making a salad or something, but you need to do something externally. Stars are similar. Cooking up a star is similar. You do need a substance, and I have a little activity for you. I have a little poll for you, and you can join the poll this way. There's also a, so if you have a phone, you can join in by text or through website, and I'm basically asking you what you think the substance in a star is. So if you were cooking a meal, or if you're eating out at a restaurant, you would expect something to fill you up. What would that be for a star? What do you think? And let's take a couple minutes, give people time to do that. Your answers should show up here. If they don't, we will change plans. But does say total results 1. It's not results 2. Doesn't seem like it's working. Oh, okay. Yeah, I had to do that. But yeah, oh, this is good. This is looking good. Brachydium? Interesting. Oh, someone sent in a smiley face as well. Cheese? Interesting. I would like a cheese star. Big, hot ball of cheese, like fondue. Let's take a couple more minutes till it like stops moving around much. Getting there. RAM. Okay, so we are gonna recoup and like look at the answers. The person who sent in presodinium has really good spelling. The person who sent in needed everything. Yeah, matter is right too. Yes, good job. It's, yeah. There are other stuff, like stuff other than matter that could form stars, but stars don't have that. Yeah. But yeah, whoever sent in hydrogen was right. That's what I'm trying to get at. But these, yeah, I will stare at it later on. Maybe not waste the time during the talk. I just like that the smiley face is just hanging out there. Maybe it was sent in with something. Oh well. But yeah, so there's a bunch of actually name of elements in here. There's literally elements there too. And we will get to like how that happens. But for now, let's just, hydrogen and the second most, like the second biggest answer, helium. You were right, and maybe you don't need this DIY talk. I don't know. Well, we'll see. Oh, wait, I need to set screens. There we go. So yes, the substance is hydrogen, but the way we will essentially make a star out of that, our recipe is essentially take a pot, fill it with the void of space, and then add gas, like mostly hydrogen, into it. You need to add more gas. This is still not enough gas. You need to keep adding gas. And maybe you are thinking at some time, like, when do we stop? Like, when do you stop adding gas? Well, when parts of it start glowing. And yeah, so it will just start glowing by itself. Like, we didn't even turn on the stove or anything, like by ourselves at least. Why does it glow? It's because the star is born. Different star in the movie, but a star is born. What actually happened is, like, the proverbial gas stove does turn on by itself. We didn't do anything other than add the gas. But let's talk through what exactly is happening in our pot of gas, hydrogen. So we did start out with, we have a lot of hydrogen in there. As you keep adding more hydrogen, the stuff that's already in there is getting squished together. And the closer all those hydrogen nuclei or atoms get, they essentially start smashing into each other. And when they start smashing into each other, they create helium. Helium was the second most answer thing in the cloud bubble stuff. But yeah, so they produce helium and a lot of energy. So that's the squiggly bright yellow lines in there, energy. Yeah. So in gas terms, we have like these parts where there's a lot more gas than the blanks up there. If we sort of zoom in, it's just like gas. But because you have a lot of stuff, it will start collapsing in on itself. That's due to gravity. That's the same force that's keeping us on Earth. We don't crash in, but there's so much gas in there that it just like starts collapsing in on itself. And then when the gas stove turns on, which is actually nuclear fusion, the energy it produces pushes back the clouds out. And because the energy is essentially getting produced as light, it starts glowing. So inside the star, though, there's a party going on, basically. So the star is, we established this before, it's huge. It has different parts to it. There's a core, there's the outer layers, we'll call it envelope, that is the technical term. There's gravity crushing it in, and the stove, the nuclear fusion, it's happening in the core. And that pushes the stuff out, which is the direction of energy flow. It flows outward from the core. And therefore you get a star. So if you had like kept on adding more mass, it had still not glowed, and like you kept doing that, like essentially if your cloud regions are more denser, like it has more stuff in a given area, it will form a bluer star. Fun fact. And if you have lesser mass, it will form a redder star. So this way, even a rookie can adjust like which type of star you get. Like you have different options. This is the part of the DIY video where it starts to get complicated. Heads up. So why do they look different? It's because their temperatures are different. So stars are hot, but you can have hotter stars and relatively cooler stars. And we'll come back to that on like what's exactly happening, why are they different. But can a rookie make complicated stars? Well, yes. Don't start with gas. Start with a star, right? So essentially, I mean, just buy a star in a store or something, and give it limited fuel. Like limit the amount of hydrogen you have in the core, which is a natural process. There's no unlimited supply anywhere. And you let it stew. For a sun-like star, the stewing time is 8 billion years before it changes into a more complicated, different star, right? And stewing time actually varies. So longer stewing times for the first process, the thing like below is the sun. That's 8 billion years of stewing time. And then shorter stewing times after that. And what essentially happens is when it runs out of hydrogen, there's nothing to hold it up, and it will start collapsing again. The star is still made up of hydrogen. There's still like gas smashing in hydrogen into itself as it collapses. So that kickstarts burning more hydrogen in the star. Eventually, you just have helium, and stewing times for heliums are just like it goes out very fast because the star is very hot right now. So essentially, how it will look from Earth as the sun goes through this process is something like this. Like the sun will expand. The core is like going in while it's pushing the envelope out. It cannot hold on to that much star anymore. And then it will get redder. It will essentially swallow up Mercury and Venus. We'll get pretty close to swallowing up Earth. We will probably be dead by then. This is not going to cause global warming and stuff. That's a more like urgent crisis. But it will get very hot. And we might be swallowed up. So a friend told me actually that there was news about a star eating up a star eating up a planet. And wait, where is my cursor? This always happens with videos. No. Yeah, so I looked it up, and it was just funny, so I included a screenshot. But yeah, I think 3 weeks ago, a month ago, astronomers actually observed this process happening in another faraway star system where the star expanded, ate up a planet. When I searched this, Google thought I wanted to look up Star Wars planets. That led me into a rabbit hole. And then there will be like sensational stuff where you see I clicked that. Why astronomers spotting a star eats a planet, bad news for Earth. It's gonna happen, but in a while, we won't be around. If you click on it, it's less sensational. So it is a very clear clickbait. Don't get roped into that. But anyway, digression. But yeah, so the type of star you begin with also changes how long it takes for it to change into a different star. And I mentioned before that burning helium takes shorter because the star is already really hot. And it's the same principle here. I briefly mentioned that the bluer star is hotter, redder one is cooler, and the stewing time varies accordingly. The hotter star spends less time burning hydrogen than a very cool redder star. Think of it as like a high flame and a low flame. Even better example, this is an actual gas stove, like a blue flame in a gas stove, whereas this is like candle flames. Like it's that different, right? It's like making soup on a candle flame, not even a burner. So it will take a lot more time, even more than the age of the universe. So the end product, the product you end up with, also will vary. For this sun, the star was red, it was big, so we call it red giant. It won't always be a red giant for all the different stars that were on the previous slides. Very dense diagram. We can still kind of see that you start with a protostar, which is our gas, like our blob of gas that's getting smushed together. And if you have bigger circular blob of gas, you end up with a blue star. But let's actually zoom in on this. So for a sun-like star, we went through this, sun-like star changes into a red giant. It will then explode out once helium finishes burning, and then it will become something that's called a white dwarf. That's a dead star, it's not burning anything, but it's so small and dense that the electrons in there that's supposed to be inside the atom, even like smaller pixel on this screen than the lab coat scientists on Earth. That's what's holding it up. Crazy. We're not going to go into that, not complicate this DI by star thing more. But yeah, so there are redder stars than the sun. Sun is kind of yellow. It just stays red. It doesn't get hot enough to ever burn helium. It will keep burning hydrogen till it becomes a white dwarf. If you add in more mass, bluer stars, it's a whole range of possibilities. So the dead stuff that they do form are either neutron stars or black holes. They do not form white dwarfs. But the process that they go through that, like to make that, varies from star to star. And all of that, we kind of, astronomers like myself, have a very neat chart where we can put all of that stuff in there and then like not have to look at anything anymore. It's called an HR diagram. There's temperature on the bottom that's like cooler stars that way, and like brighter stars are up. So you see like giants in there. That's the red giant that we were talking about. There are supergiants, like red supergiants. So they are still red, but they're bigger. They're the biggest stars we know of. And if you can track how a star evolves into a different star throughout this diagram. So just to make sense of the vertical axis, you have the sun. Lower stars have like less brightness than the sun, so like 1,000th time, one by 1,000th of the sun is like down there. We are going pretty abstract. Again, complicated parts of the DIY process. But the sun is here. It will go up the red giant branch and then become a white dwarf. A rookie only needs to know that, so we won't go deeper. Unless you have questions, then catch me after the talk or ask me questions later. Something that's less bright than the sun, has less mass, and it will just end up as a white dwarf, right? It won't do much. Something that's bluer will go into the supergiant regime, and that will end up as a black hole or neutron star. So you can essentially, like everything is in there, except black holes and neutron stars because they aren't that bright, like to the human eye. This is like all people can see. And if you like draw, this is just for conceptualizing, like if you take all masses and like keep drawing squiggly lines on like how things move, this is kind of what it looks like. The point I want to make is less squiggles down, more squiggles up. So the star is doing a lot more thing. It sometimes goes like redder and then bluer, and like there's more complicated physics happening that essentially commands that. But the HR diagram is a good recipe card for you to keep in the kitchen while you're making your DIY star. So we currently have a really bland star. I mean, we're just like adding in gas and nothing else. So what spices should you use? How to flavor up your star? Basically, how to control these complicated squiggly lines on there so that you get more interesting stars. Well, premix store-bought blends work fine. And let's explore some options that we have. So remember, like we have been talking about hydrogen atoms getting smashed and so on, but that's only like a good description for a simple star. For both of these stars are burning hydrogen, and it may look like the same spice, but it has different names because a different process is occurring. This is like sugar and salt look the same, but they are two different flavors. This CNO cycle labeled here for the bluer star takes a higher temperature to happen than the proton-proton chain that is happening for a lower mass, lower stuff, lower flame star. For helium, it's a whole different name, like that's a different color there. It's called a triple alpha process. But this is like divulging into complicated stuff, not good for rookies. So there's something called stellar evolution codes that we use. I mean, by we, I mean stellar astrophysicists, the experts. So there's, this is from the MESA website, and this is, I don't think they know about no-frills. But yeah, they have a no-frills hydrogen and helium burning, so you can use like a no-name brand hydrogen fusion mechanism. You just have to type in basic, and it will just do everything for you, right? You don't have to worry if the star is burning helium or hydrogen, which process it's going, which spice it's using. You just like put in basic, it does everything for you. If you are the person who answered hydrogen and helium in there, maybe press the dominium. As in, if you have more interest in chemistry, there you can like control how the stuff is burning in there. So all this like alpha stuff is like how carbon and oxygen are burning, how helium is burning, and so on. You can add in like what stuff in the star controls what. Like you get a lot more freedom. But yeah, if you're a rookie, just do the basic and like be done with your life. Like go do other things. But yeah, so you have, if we have more spice options, we have more flavors. And we have just talked about the nuclear fusion process. So there's a lot more happening in the star. Like the star has a structure, and each of it behaves differently. Like see, there's like straight lines there, and there's squiggly lines there, different things happening. So this, like stars also have atmospheres. Like the Earth, it's the outermost very thin layer of gas in there, but star is almost entirely made up of gas. So that makes things even more interesting, like different from Earth. So you can set what kind of atmosphere you want, and that's even more spice options. So I mean, I'm not gonna describe what like a Paczynski gray atmosphere is to you. I don't even know what it is actually. I don't work with stellar atmospheres much. But like fixed pressure is like, what if I fix how much like the star is exerting force on the outer layer, and then everything evolves in there differently. I don't control it, but that will give you like how different the star looks and so on. Essentially, the star keeps readjusting to the constant force of gravity trying to crush it. So it will change how the energy from the core is getting transported out. And that changes how the star behaves, how the star evolves, and so on. And this gives you that much freedom to like essentially micromanage your star. There are a lot more options. That I just walked you through one. All of these are drop downs. There's a plus sign there. So you can like change the chemistry of the star. You can change how does the star transport light and energy inside it. Like is it like boiling a pot of water versus is it like going on a barbecue? Like it's different processes, different outcomes. And the nuclear ones are of course your gas stove control, like high flame, low flame, which process, what is actually fueling your star and so on. But yeah, it's like a spice aisle, and like Emily on Twitter, it also gives me anxiety. But we talked a bit about all of this, and I mean, I'm sure at this point you understand this is a complicated process with a lot of nuance, and while you can get away with doing the most basic thing, you're probably not creating the most realistic thing, and they won't give you a PhD for it. I have tried, I will mention. So what does an advanced DII guide look like? Like what if you were a grad student studying this? So let's circle back to the scientific method, right? After we simulate, we should probably go to analysis and conclusion, right? Like see if our models make sense according to what we hypothesized, and then conclude. Actually, it's not that simple. It's more like this, where like if you put the scientific method on the wall instead of the other papers, that's how I look like on the daily. I do not smoke though. But the reason behind that is that switching your spices significantly changes things. And I've been saying that for the past 10 minutes probably. So essentially, once you have your simulations done, your analysis is usually a big red, because you want your simulations to look like the real stuff. That's the whole point. Recreating a star in a lab, you can't do that, so you do it on your computer. It usually ends up not matching. So you keep going back and forth between like, do we match the observations? Oh, no, we don't. Change the spice blend. Do we match the observations now? Oh, no, we don't. And then we need to constantly review our spice blends because, I mean, we are not using the pre-mix store-bought blends, right? We are the ones making them, which is worse. So, because even a minor like thing will change how the whole flavoring looks like. For instance, stars rotate. Like the most familiar example of rotation of like a really large body of rotating stuff is the Earth rotating. It causes day and night. Stars actually don't exactly rotate like that. They have layers. So like the core would rotate differently than the envelope, and the atmosphere would rotate differently. It's like if you had an onion, you spin it, but the insides of the onion move differently than the outside. So stellar rotation causes the stars to do different squiggly lines on our recipe card, right? And these are two different models. And I would just like to point out they don't agree. The paper I took this from was like the MIST models, right? And they say that the Geneva people are right. So when you have academic folks admitting in their paper that they are wrong, you know something is up. So we get stuck again at the simulate process. Go back, change your hypothesis because you were probably wrong about that. Then go simulate again, and then like keep going back and forth between the process. What about observations? Are we still matching observations? Well, with rotation at least, we didn't really have data for a really long time. Like most of the physics, most of the spice blends that we came up with were in the 20th century. And most of our telescopes that are giving us data on how stars rotate, other than the sun. And we established like, if it's not the sun, it's like doing different things, right? You can't just keep looking at the sun. The earliest one was 2009. We are still like coming up with new theories on like, we still haven't explained that 2009 to 2018 stuff. LIGO gives you like black hole and neutron star rotation or like spin data and stuff that started giving data in 2015. TESS has been around since 2018. And yeah, observations keep updating. So we have to update our prescriptions. It usually ends up only fixing one part of the problem because, so they found out black holes are rotating slower. Then the same people came up with, oh, this is why they would rotate slower. I work on sun-like stars, and I have a completely different thing that I am working towards a paper on, and it's different from what they're saying. So that's gonna change what these people said about like stars like the sun that do not form black holes, but they are also slow rotating. It's not even straightforward. Your data has different stuff. Again, same people now being like, hey, wait a minute. There are some black holes that are actually rotating faster than we thought they were. What is happening there? So we don't have a full picture of it planned out because it's a bit of a scamper in the sense of like, we had our models for a really long time. We don't know how stuff was out in the universe. And now that we do, we're trying to catch up. So it's essentially a game of whack-a-mole where you solve one thing, but then another thing pops up, and then you're trying to like solve another thing. But yeah, another example is stellar winds. I also work on this. So stellar winds are essentially not like Earth winds. It's the star chucking out gas into space. Sometimes like sun does that too. Sometimes it reaches Earth. If you're familiar with the aurora, the northern lights, it causes power outages sometimes, but it looks really pretty. But that is a consequence of the Earth trying to combat like sun's winds, solar winds. But again, like more massive stars, like the red supergiants up there, have the strongest winds of sorts. And it's a completely different physics that we do not understand why it happens. It's different from why it happens in the sun, right? This is what a red supergiant looks like, by the way. Or actually, this is an artist's impression. We do have an actual image. This is based off. The actual image looks like this. But yeah, so sun is like that 1 pixel in there. And yeah, both Betelgeuse and Antares are red supergiants. They are big stars. They are very different from the sun. But yeah, the last time there was a significant recipe, so to speak, of how stellar winds work was 1988. 32 years later, in 2020, January, another paper came out that said, well, we don't think the 1988 paper was right. So we have this like new data. We don't understand how red supergiants work. We had different observations to like essentially make up a splice blend. We can't do it on our computers by ourselves. And that doesn't get done for 32 years. That's older than how old I am. So what they essentially said was that our models that was based on the 1988 spice blend, sounds like a wine. Anyway, models thought that the star is losing about 15 suns worth of mass. Again, sun very big, that is a lot of mass. But the new data says, oh no, it actually probably only loses like 1, maybe 2 suns at best. This is a huge jump. That is going to change how the star evolves. So my current task essentially, or part of my task is updating that for certain systems. And we are once again stuck at this, like, we are not simulating things right. Let's update our simulations. Is it gonna match the observations? Probably not. I haven't gotten there yet. A paper is about to come up. But what I am specifically updating this on is something called binary stars. And this is like stars that have a companion close to them, like say Sun and Jupiter distance type of stars. And if the Sun was a red supergiant and was losing less mass than we thought it was, what would it do to Jupiter? Like, that's the kind of stuff I work on. But yeah, so far it's still been that, because then you need to make sure that you are capturing the physics, the spice blends of a binary system well, not just a single star. And then you essentially still keep going back and forth between how things work, if they are matching observations. And yeah, that's why I have a job, and that's why most of us have a job. But yes, that is all I had to say. Good questions.
Thank you, Eesha, for that very interesting talk. We have lots of time for questions, so you can raise your hand if you have a question, and then if you could please repeat the question before answering it.
Oh, I see a hand raised there.
What's in a white dwarf after the star dies?
Okay, so the question is, what's in a white dwarf after a star dies? So there are actually 3 possibilities. I told you about the red dwarf that doesn't do much, like it can only burn hydrogen and then it becomes a star, right? Sorry, a white dwarf. So that type of white dwarf will only have helium in it. The kind of white dwarf the sun forms will have carbon and oxygen in it, because the sun is capable of burning helium. And there's also another kind of white dwarf that I don't think they found yet. It's oxygen neon white dwarfs. I'm not too sure on like, yeah, I'm shaky on that because I don't work on it. But yes, so 3 types of white dwarfs. Good question, yeah. Question there.
Do white dwarfs still have any fusion happening inside? And if not, do they give off any light? And if they do, why?
Yeah, so the question is, do white dwarfs have any fusion happening? And if not, why are they giving off light? And I will take you back to the HR diagram actually. White dwarfs are on there. So this is everything a human eye can see, right? Or, well, we are a bit shaky on the redder and the bluer ends. but it's still like, you can technically see a white dwarf. Why are they giving off light? And yes, no fusion is happening. But it's a bit of a quantum mechanical thing. When white dwarfs are really dense, so what's holding them up essentially is because you cannot squish two electrons together. So if you go down to like that size, it's not like this mic is a thing and it has a place, right? Electrons, if you like zoom in, are a bit shaky. You can't like push them together. You can't squish them together, which means they'll resist getting squished together. And it's called something called electron degeneracy pressure, and that's what holds the white dwarf up. And that's what is responsible for a white dwarf basically existing and not imploding in on itself. And that produces energy. Yeah. There's a question there. Yeah, good question. Okay, so the question is, what happens in a black hole? People are doing PhDs on this. What grade are you in? I just want to. 4? Great, you have a lot of time, figure that out. Sorry. But, so essentially, black hole is, I told you a bit about gravity, about how it's always trying to collapse stuff. And black holes are getting formed of stars that have a lot of stuff that's getting collapsed, right? So it's basically a point that like sucks up everything if you get close. This applies to light as well, that like there's kind of a point of no return. And if you, like beyond that, even light can't escape. So it's basically a vacuum cleaner of space, if that makes sense. Yeah, a lot of like sucking in vacuum stuff is happening inside a black hole. Yeah?
Thank you. What is the actual color of the sun? I thought it was white, but based on this, the sun seems to be more yellow.
So, I'll repeat your question. Let me know if I got that right. Why does the...
What is the real color of the sun?
What is the wind color of the sun? The real color of the sun. So it is kind of yellow. So one thing you'll notice is that this is like a rainbow, but there are no green stars in there, right? The rainbow has green. We can go back to our Pride logo to show that. But sun is kind of on the borderline of like yellow to white switching things. The way the sun appears from the earth is also because the atmosphere, Earth's atmosphere is reprocessing the sun. So the sun looks redder in the evenings versus it looks whiter during the day. But yeah, the real color of the sun is more yellowish. It peaks around there, around that color, like a yellow-white color.
So does that mean that in maybe 1 million years from today, if you try to repeat like Newton's experiment, do we still have like the light going in different shades, rainbows color, if the sun already moved to more yellow, more red?
So give it 8 million years. No, wait, we are at the 4 million year mark. 4 billion year mark.
So to say if we are far,
Oh, okay.
and the sun already moved in one of these zones in this map,
Mm-hmm.
can we still say that like the light is based on the rainbow color at that moment?
Yes, because so stars are something called the black body, as in you can see them. Say if you had a telescope that only looks at this region, you will still see the sun. It will be very dim. And if you have a telescope that looks like only blue, it will still see the sun, but it will also be very dim. It will be the brightest around the yellow part, which means all stars are capable of creating rainbows. The way a rainbow happens, though, is again reprocessing the light of the sun. So if you were out in space and there was like the void of space that we started out with in our pod, you won't necessarily see a rainbow there has to be something that's like altering and like splitting the colors. But yes, even after like it becomes a redder star, it will still like have the rainbow effect going on. Yes. Yes.
Possible for one of the suns to like change its color for us not to perceive it anymore?
Right. So the question is it possible for any star to change its color and so that we don't perceive it anymore? So that's what happens to black holes. It's not changing its color. It's just not giving off any light. Like everything just imploded. You don't have electrons holding it up. You don't have the nucleus holding it up, which neutrons hold up a neutron star. But like, yeah, everything just imploded and you can't perceive it anymore. There are also something called a black dwarf that's essentially a white dwarf fading out. But that's, I'll have to see if we found any or if it's a theoretical thing. But yeah, so if essentially you run out of fuel completely and there's nothing like that's reprocessing stuff to hold the star up, it won't give off any light and we can't see it. Oh, you have another question.
What happens when the sun is far away from Earth?
We die. But okay, so the question was what happens when the sun is far away from the Earth? I mean, just say like the possibility of that happening is very slim. Like there's nothing that will chuck the sun out. We are in a very calm place. If that were to happen, the planets would suffer, as I made it clear. The sun would probably be okay. The sun would probably be okay. So, yes.
You mentioned this, but so why does the sun seem whiter when it's at the top of the sky in the day versus more red in the evenings?
Right. So it's essentially how the light is interacting with our atmosphere. So the gas we had like little hydrogen balls, right, that were getting smashed in. Our atmosphere has a lot of nitrogen, and that is reprocessing the light differently. So it's a process called scattering. So it scatters out pretty much every light the same amount. And if you mix all of the light in the rainbow together, like if you smush it together, you perceive it as white. So, which is essentially why the sun looks whitish if it is up in the sky.
I'll draw a picture to help.
Yeah, go ahead.
Earth and the atmosphere.
I forgot we had a blackboard. I could have done this before.
Yeah, there's the sun. The light goes through a small amount. Versus if it's over here. There. Then this whole.
Yeah, exactly. So here the sun seems redder. When it's like dawn, dusk, sunrise, sunset, it's at the horizon. That means almost everything is getting scattered out except red, if I'm right. So that makes the sun look redder. But when it's up here, it's like, everything is getting scattered the same amount, which is why it looks white.
There's less atmosphere.
But there's less atmosphere, yeah.
So
So
you see what's scattering the most.
yeah.
So what is the atmosphere changing? Like what did you say you're not including in the color if it travels through the atmosphere?
Like essentially the sky looks blue here because of like less atmosphere traveled through. And the sun looks whiter because it's a smush of every color it has. But here, since you're spending longer time going through the atmosphere, it's reprocessing the light a lot more. And by the end of it, like it has reprocessed almost everything on here and only red is left, kind of. Yeah. Yeah.
A black hole is not a black hole, it's a black star.
Okay, so the question is, a black hole is not a black hole, it's a black star. I think the naming mostly comes from the fact that it's something like a hole in space and time. It's like, you had a lot of stuff and it imploded in. Essentially, it got sucked in. there was nothing to resist it out. So it's not giving off any light because it's sucking light in. That's why it's black. And it's a hole because the way you would see it is like blackboard. So if you were to like look at a black hole from the outside, here is the actual like point where everything imploded. And again, so star is something that has structure. It's a sphere almost always. A black hole is like everything got smushed into a point. That's why it's like a point object. It doesn't have any dimensions. It's just really hard to comprehend for like people like us who think in 3 dimensions. But even light is getting sucked in, and the point at which, say, I have light going in, and it gets like around here, and beyond it, it's all dark because like light doesn't make up. This is called the event horizon. So the way you see it from here would be like a static thing here and nothing beyond what happened. So it looks like it got sucked into a hole. So yeah, that's why it's a black hole, not a black star.
I think we have time for one more question.
Sweet. Any last minute questions? Okay.
So how do we know that in the black hole there isn't fusion happening? If you're sucking in that much matter, why isn't it?
Right.
Somewhere if you're sucking in so much, that amount of fusion, should it not explode like the stars are?
Right. So I'll repeat the question. How do we know fusion isn't happening in there? It's not like we can see it. What if it's doing fusion in there and we just don't know because we can't see? So when a star does fusion, it pushes matter out. The whole point of fusion happening in a star is because it wants to resist gravity. For a black hole, what really matters here is that gravity takes over. That's why like it's not an explosion, it's an implosion, if that makes sense. So it's like imploding in. If fusion was happening, it would push stuff out. It won't be a hole. It won't be one point where stuff is going in. If that makes sense. So it's actually the exact opposite thing happening. And because it's sucking up everything without nothing get pushed out, we know there's no processes happening in there that can chuck stuff out, that can explode, proverbially. So no nuclear fusion is happening in there, for sure. Yeah.
Great. Thank you very much, Eesha. Very interactive talk. Okay, so before we go to the event, say a quick thank you to all of our volunteers and our sponsors for allowing this event to happen. And now, that says 10. That should say 10:30. Sorry about that. We will be heading over to the physics building. There will be volunteers in the lobby wearing shirts like this that will bring you over to the physics building. And that is where we will be having the telescopes and such.